This video will discuss the Gibbs entropy, which is a formula that determines the entropy of systems which have different probabilities in statistical mechanics. Alright, so we saw in the previous video that if the energy of two states is equal to one another, then the probabilities of the system being in that state is also equal to one another. And from our previous statistical mechanics experience, we saw that if the energy of state 1 is not equal to the energy of state 2, then the probability of of the system being in that state is proportional to the Boltzmann factor, e to the minus energy of that state divided by Boltzmann constant times temperature. So lower energy states are preferred, and having a higher energy than the ground state has an exponential penalty as you increase in energy relative to kT. So the absolute probability of a given state was determined by 1 over the partition function times e to the minus beta ei, where beta was 1 over kT, so this is still the same Boltzmann factor there. And this partition function could either be written as a sum over all states accessible to the system of the Boltzmann factor of each state, e to the minus beta ei, or as a sum over all energy levels of the degeneracy, the number of states in each energy level, times the Boltzmann factor of that energy level. All right, so what we have here in the previous video, we looked at the entropy that occurs when all the states have the same energy. But in most cases, many energy states have different energy levels, so we need a general formula that gets us the entropy based off of varying probabilities due to differing energies. So that general formula is the Gibbs entropy formula, and that says that the entropy of a system is equal to the negative Boltzmann constant times the sum over all states of the probability of that state times the natural log of the probability of that state. Okay, so you probably don't have an intuitive feel for what this function looks like right now. This looks like minus k sum x log x. All right, so let's look at some cases. So if the temperature equals 0, then the probability of the lowest energy state, the ground state, equals 1, and the probability of every other state is 0. So the entropy at t equals 0 is just going to be the Boltzmann constant times the natural log of the degeneracy of the ground state, if you substitute in this kind of formula there. For most cases, for most atoms and molecules, the degeneracy of the ground state is 1, so the natural log of 1 is 0. So for most systems at 0 Kelvin, our entropy is going to end up being 0. So at 0 Kelvin, we end up getting pretty much 0 entropy unless there's some degeneracy of our ground state greater than 1. All right, if t equals infinity, then all of our Boltzmann factors here just go away to 1. So all the probabilities become equal when the temperature is infinite, so pi equals pj for all I and j. So in that case, if you substitute in there, what you'll get is that the entropy is just equal to the Boltzmann factor times the natural log of the number of states. So if we have n degenerate states, then the probability of each one of those states is going to be 1 over n, and you'll get a value that sums up to this, as I said. So when we do that, the entropy equals minus kb, sum from I equals 1 to n, 1 over n log 1 over n. So we get, for all n there, we're going to get minus kb log 1 over n, and then the natural log of 1 over x is minus natural log of x, so the minus sign there is going to cancel with this one. We're going to get the Boltzmann constant times the natural log of n. And as I said, for one state, s equals kb log 1 equals 0. So if our if our system is entirely located in one state, then the entropy is going to be 0. If our system is equally distributed between all available states, then the entropy is the Boltzmann constant times the natural log of the number of states. And at all finite temperatures in between, the entropy lies somewhere in the middle. So as I saw there, at 0 Kelvin, it's kb times the degeneracy of the ground state. At infinity, it's kb times the log of degeneracy of all the states. And in between, it's somewhere in between. So what the entropy really is a measure of how well distributed the energy is, or how well distributed the system is between all the available energy states. So the higher the entropy is, the more well distributed, the more even the probabilities are. And the lower the entropy is, the more uneven, the more concentrated, the more undistributed that the energy is. All right, so some numerical examples of this formula. If you plug in these probabilities into this formula and do the sum, the entropy I have it divided by KB here. So this is in units of Boltzmann constant. So take these numbers and multiply them by KB, you'll get this number. So as I said, if you have a single state with a probability of 1, you'll get an entropy of 0. If you have two states of 0.5 each, you'll get natural log of 2, 0.693. 3 states that are equal, natural log of 3. 4 equal states, natural log of 4, etc., as you go. If you have one state with 0.99, 99% in one and 1% in the other, you get almost 0, but not quite, 0.056 KB. 90% in one and 10% in the other, you get much more entropy, 0.325. And then 0.75 to 0.25, you get much closer as you're approaching equal probabilities there, much closer to the equal value. If I just have a smattering of them there, 6 states of kind of exponentially decreasing probability as I go, I get 1.357. I can plug in any set of numbers I want. You can just see what the values end up being there. So the real takeaways here are that based off the probability of each of the individual states that we have the Gibbs entropy formula for what the entropy of the system is. It varies from the value at 0 Kelvin, which is a minimum, up to the value at infinity, which is a maximum, and at all temperatures in between, there's some value which lies between those two extremes of the most concentrated and most well-distributed states for the energy of the system.